Basic constituents of communication system. Basic elements of communication system are transmitter, channel, and receiver. Transmitter is a device that converts the information into electrical signal. Channel is a physical medium that carries the electrical signal. Receiver is a device that converts electrical signal into original information. Modulation. Modulation is a process of varying one or more properties of carrier signal with a modulating signal. Need for modulation. It is needed in order to match the characteristic of input signal to that of channel characteristics. Multiplexing is made possible due to modulation. Wireless transmission. Low pass signal is made possible due to modulation. Some modulation techniques reduce the effect of noise and signal. Practically realizable antenna size can be achieved. Message signal is modulating signal. It modulates carrier signal. Modulation, some properties of carrier signal are varied in accordance with the message signal. Carrier frequency is much higher than message signal frequency. Baseband signal is a signal having significant frequency component near to zero. Hollow frequencies. Band pass signal is a signal having significant frequency component all the way from zero frequency or low frequency. Spectrum means frequency domain representation of signal. Noise is mainly added to a signal. The channel bandwidth of a signal is defined as band of group of frequencies for which amplitude of signal is not zero. Time domain representation at Vc equal to Vc cos omega ct, Vm equal to Vm sin omega t. Then amplitude modulation signal is S of t equal to Vc into 1 plus Vm by Vc cos omega mt into cos omega ct. K equal to Vm by Vc is called modulation index. K equal to Vm by Vc. S of t equal to Vc into 1 plus k omega mt into cos omega ct. Bandwidth equal to Fc plus Fm minus Fc minus Fm equal to 2Fm. Minimum value of amplitude of modulation of amplitude modulated wave is V minimum equal to Vc minus Vm. Maximum value of amplitude of modulation wave is Vmax equal to Vc plus Vm. Modulation index in terms of Vmax and Vmin is K equal to Vm by Vc equal to Vmax minus Vmin by Vmax plus Vmin. For avoiding phase reversal, modulus of K less than 1. Power relation AM wave PAM equal to V square carrier by R plus V square LSS by R plus V square US by R. V carrier equal to VC by root 2. PC equal to VC square by 2R. Where all the voltages are RMS voltages, RMS resistance of the antenna across which power is dissipated. Similarly, PLSB equal to PUSB equal to VSSB square by R equal to K into VC by 2 whole by root 2 whole power square into 1 by R. PLSB equal to PUSB equal to K square VC square by 8R. PAM equal to VC square by 2R plus K square VC square by 4 into 2R plus K square by 4 into VC square by 2R. PAM by PC equal to 1 plus K square by 2. 1 plus mu square by 2. Maximum power dissipated by AM wave is PAM equal to 1.5 times that of PC for K equal to 1, and this is maximum power that the power amplifier can handle without distortion for a sinusoidal carrier. Current relation in AM wave. Let IC be the unmodulated current and IT the total or modulated current of an AM transmitter, both being RMS values, and R is the resistance in which current flows. Then PAM by PC equal to IT square R by IC square R equal to 1 plus K square by 2. IT square by IC square equal to 1 plus K square by 2. IT by IC equal to root over 1 plus K square by 2. Modulation by several sine waves. Let V1, V2, V3 and so on etc. be the simultaneous modulating voltages, and the total modulated voltage Vt will be Vt equal to root over V1 square plus V2 square plus V3 square and so on. Vt by Vc equal to root over V1 by Vc whole square plus V2 by Vc whole square plus V3 by Vc whole square and so on. Kt equal to root over k1 square plus k2 square plus k3 square and so on, where kt is overall modulation index, k1, k2, k3 are respective modulation index for individual waves. PAM equal to PC plus PC k square by 2 equal to PC plus PSB, where PSB is the total sideband power. PC kt square by 2 equal to PC k1 square by 2 plus PC k2 square by 2 plus PC k3 square by 2 and so on. Double sideband suppressed carrier DSBSC technique. S of t is a DSBSC modulated sine signal. Then S of t equal to Vm cos omega ct. S of t equal to Vm cos omega ct into cos omega mt. S of t equal to KVC cos omega ct cos omega mt. Frequency spectrum of DSBSC wave. Bandwidth equal to 2Fm. Power relation PDSBSC equal to PUSB plus PLSB. PUSB equal to PLSB equal to K square VC square by 8R. PDSBSC K square VC square by 4R P DSBSC K square by 2 into PC. 66% of power is saved in DSBSP compared to AM due to absence of carrier is modulated wave. Single sideband technique, SSB technique. A single sideband SSB AM signal is represented mathematically as S of t equal to Vm cos 2 pi fct minus plus Vm cap sin 2 pi fct. Vm cap equal to Hilbert transform of SS signal. Vm minus means signal represents USB plus represents LSB. Frequency spectrum of SSB. Power relation in SSB wave PSSB equal to VLSB square by R equal to PUSB square by R. PLSB equal to PUSB equal to VSSB square by R. PSSB equal to K square by 4 into VC square by 2R. PSSB equal to K square by 4 into PC. Vestigial sideband VSB modulation techniques. Mathematical representation of VSB wave is S of t equal to Vm by 2 cos 2 pi fct plus minus Vm comma q by 2 sin 2 pi fct. Vm comma q equal to quadrature phase component of Vm. Frequency spectrum of VSB wave. Power relations in VSB wave. PVSB equal K square by 4 into PC plus F into K square by 4 into PC, where F equal to represents a fraction. A modulators and demodulators. Square or power law demodulation, power law modulation is used for generation of AM waves using nonlinear devices. Switching modulator is also used for generation of AM waves. Balanced modulator and ring modulators are used for generation of DSBSC waves. SSB waves is generated using analog multiplier and band pass filter. Filter method and phase shift methods are also used for generation of SSB waves. Analog multiplier is also used for generation of VSB wave. Envelope detector it is used for detection of AM waves. R of t is received signal, M of t is message signal. For better reception of RC must be selected so that 1 by FC less than RC less than 1 by W. CNRL parallel డయోడ్ పెడతాం సిఎన్ఆర్ఎల్ ప్యారల్ పెడతాం రెసిస్టర్ దగ్గర ఎంఆఫ్టీ తీసుకుంటాం డయోడ్ ముందు ఆర్ఎఫ్టీ తీసుకుంటాం వేర్ డబ్ల్యూ is bandwidth of message signal. Demodulation of DSBSC and SSB waves is done using coherent carrier signal at receiver. Envelope detector can also be used to recover message by passing received USB signal through it. RC max equal to root over 1 minus k square by kW to avoid diagonal clipping where k is modulation index. Comparison of different AM techniques. Modulation technique AM total power PC plus PSB bandwidth equal to 2 omega application medium wave short wave. DSBSC total power PSB bandwidth 2 omega application no application. ESBSC total power PSB by 2 less than PT less than PSB bandwidth omega m less than bandwidth omega m less than bandwidth less than 2 omega m application picture signal in TV, whereas SSBSC has total power of PSB by 2 has bandwidth of omega m has application of telephony. The omega m message bandwidth signal percentage of power is DSBSC modulation compared to AM equal to 2 by 2 plus k square. Percentage of power saved in SSCS. Percentage of power saved in SSC modulation compared to AM equal to 4 plus k square by 4 plus 2k square. Angle modulation. Angle modulation consists of frequency modulation FM, phase modulation PM. An angle modulated signal in general can be written as U of t equal to cos theta of t, with theta of t is phase of a signal, instantaneous frequency, Fi of t equal to 1 by 2 pi d by dt of theta of t. Phase modulation is a process in which phase of the carrier is varied in accordance with baseband signal. The standard equation for a PM signal S of t equal to AC cos omega ct plus kp m of t, where omega c is carrier frequency, m of t is message modulating signal, kp is phase sensitivity, radians per volts. Instantaneous phase phi a of t equal to omega ct plus kp into m of t. Instantaneous frequency omega a equal to omega c plus kp into d by dt of m of t. Phase deviation delta phi equal to kp m of t. Frequency deviation delta omega equal to kp d by dt of m of t. Deviation ratio beta p equal delta omega max by omega m, that equal to kp into d by dt of m of t by omega m, d by dt of m of t max, where omega m equal to message signal frequency. Frequency modulation, it is a process in which frequency of carriers is varied in accordance with baseband signal. The standard equation for a FM signal S of t equal to AC cos omega ct plus kf integration of m of t dt. Instantaneous phase phi a equal to omega ct plus kf integration of m of t dt. Instantaneous frequency omega I equal to omega c plus kf into m of t. Phase deviation delta phi equal to kf integration of m of t dt. Frequency deviation delta omega equal to kf m of t. Deviation ratio beta f equal to delta omega max by omega m equal to kf m of t by max by omega m. For PM, in case of tone modulation, deviation ratio is independent of message signal frequency. For FM, in case of tone modulation, deviation ratio is inversely proportional to message signal frequency. For low value of beta less than 0.6, angle modulation scheme is called narrowband angle modulator scheme. Narrowband FM is similar to AM. It is used in mobile communication. For large value of beta greater than 0.6, angle modulation scheme is called wideband angle modulation scheme. Bessel representation of PM and FM signals. Modulated signal can be written as S of t equals sigma n equal to minus infinity to infinity AC Jn of beta cos 2 pi f of Fc plus nfm into t, where Jn of beta is known as Bessel's functions of first kind of order and total power carried by the signal Pt equal to AC square by 2 sigma n equal to minus infinity to infinity Jn square of beta. Total bandwidth requirement for angle modulated signal is infinite. For beta equal 2.4, 5.6, 8.6, 11.8, J0 of beta equals 0, implying power carried by carrier term reduces to 0. Bandwidth of angle modulated signals. In general, the effective bandwidth of an angle modulated signal, which contains at least 98% of the signal power, is given by Casson's formula BC equal 2 into beta plus 1 into FMH. Beta means modulation index. Angle modulators and demodulators. FM wave can be generated using VCO called direct method. FM wave can be generated using varactor diode called indirect method. FM and PM both can be generated using reactance tubes. Another method, you first generate narrow band FM, then pass through its frequency multiplier to produce wide band FM. Demodulation normally done using PLL, phase lock loop. Consists of double balanced mixer, low pass filter, voltage control oscillator. PL is used for FM modulation, FM demodulation. Remember, the relevant equations are S of t equal to V naught into sine of 2 pi FCT plus phi S of t, where phi S of t equal to 2 pi kf integration of m of t dt. R of t equal to sine of 2 pi f naught t plus phi I of t. Phi I of t equal to 2 pi k integration of V of t dt. Of t d equal to kf by kl m of t dt. V of t equal to kf by kl m of t, where S of t is FM signal, M of t is original signal, FC carrier frequency, F naught PLL's unlocked frequency or free running frequency, KF FM frequency sensitivity, KL VCO's frequency to voltage conversion gain value. The following conditions must be satisfied for effective demodulation. The loop gain must be very large. The loop maintains VCO's output and signal phase effectively in quadrature. Lock range is the range of input signal frequencies over which the lock remains locked once it has captured the input signal. Capture range is the range of input frequencies around the VCO center frequency onto which the loop will lock when starting from unlocked condition. Capture range is always less than lock range. The system can only lock onto an input and demodulate it if the signal frequency is such that delta f greater than or equal to b, where b is bandwidth of the loop filter. Input multiplier n, output parameters, carrier frequency multiplier input fc multiplier output nfc, modulated frequency fm multiplier output fm, frequency deviation delta f multiplier output n delta f, modulation index beta multiplier output n beta. Effect of noise on analog communication systems. Noise and another signal which disturbs the transmission and reception of a signal in communication systems. Noise, there are external noise, atmospheric noise, solar noise, industrial noise. Internal, short noise, Richter or Johnson, or thermal noise, flicker noise. Short noise arises in electronic devices because of discrete nature of current flow. Its PDF is Gaussian with zero mean and PST is constant up to 100 MHz. Thermal noise is due to random motion of free charged particles in a resistance. Vn, Rms equal to root over 4k Tr delta F, where T means ambient temperature, R means resistance, delta F means bandwidth. White noise contains all the frequencies with equal amount of power. Its PSD is constant. Data correlation is impulse at origin. Effect of noise on a baseband systems. SNR of a baseband system is given by S by N naught of B equal to PR by N naught W, where PR means received signal power, N naught by 2 means two-sided noise spectral density, W means message signal bandwidth. Effect of noise on DSBSC AM. For coherent receiver, SNR of the output is S by N of 0 equal to AC square PM by 2W N naught, where PM means message signal power, AC means carrier signal amplitude. PR equal to AC square PM by 2 received power for DSBSC carrier receiver. S by N naught DSB equal to PR by N naught W equal to S by N of B. In DSBSC, the output signal to noise ratio is the same as the signal to noise ratio for a baseband system. Therefore, DSBSC does not provide any signal to noise ratio improvement for a baseband communication system. Effect of noise on SSBAM. For coherent receiver, S by N of 0 equal to SSB equal to AC square PM by NRW, SNR at the output. AC square PM by NRW, SMR at the output. PR equal to AC square PM, S by N naught of SSB equal to PR by N naught W, S by N naught of B. SNR in case of SSB is same as that of DSBSC and baseband system. Effect of noise on conventional AM. SNR for coherent modulator is S by N of 0, AM equal to AC square K square PM by 2 N naught W. SNR at the output. AC means amplitude of carrier wave, K means modulation index, PMN means normalized message signal power. PR equal to AC square by 2 into 1 plus K square PMN. S by N naught of AM equal to K square PMN naught by 1 plus K square PMN into PR by N and W. S by N output of AM equal to eta into S by N of B, where eta equal to K square PM by K square PMN plus 1. SNR of conventional AM is always less than the SNR of baseband system. Effect of noise in angle modulation. Noise spectral density of the output of an angle modulation receiver is SN naught of F equal to M naught by AC square PM. For PM, phase modulation. For modulus of F less than W, N naught by AC F square for F for FM for modulus of F less than W, where N naught by 2 is a two-sided power spectral density of noise. Effect of noise is independent of frequency for PM systems. Effect of noise is more at higher frequencies and less at small frequencies for FM systems. SNR output for the angle modulation system is S by N naught of equal to Kp square AC square PM by 2 N naught W for PM. PM is message signal power. S by N of 0 equal to S by N of equal to 3kF square AC square PM by 2W square N naught W. 3kF square AC square PM by 2W square N and W for FM, where AC square by 2 is the received signal power PR. For PM signals, S by N signal noise ratio of output equal to PM beta square S by maximum of M of T square N of B. For FM systems, S by N of B equal to 3 PM beta F square by maximum of M of T whole square into S by N of B. Both PM and FM systems output SNR is proportional to square of modulation index. With increasing beta, without increasing the transmit power, we can increase signal to noise ratio at output. Increasing beta will increase the bandwidth requirement for transmission, so we are increasing SNR by increasing bandwidth. Remember, increasing signal power at transmitter will increase the signal to noise ratio at output. The mechanisms are totally different. In AM, it is due to increasing the signal power, but in case of angle modulation, it is due to decreasing the noise power. Noise power at the output of receiver. In case of FM, high frequency component suffers from more noise, so pre-emphasis and de-emphasis is used to increase the signal to noise ratio for FM system. In pre-emphasis, we amplify high frequency component, but low frequency components amplitudes are unchanged. In de-emphasis, we de-amplify higher frequencies amplitude, keeping low frequency amplitude same. Pre-emphasis and de-emphasis filter characteristics. Transfer function of pre-emphasis filter is HP of F equal to 1 plus J into F by F naught. HP of F equal to transfer function de-emphasis filter equal HD of F equal to 1 whole capital by 1 plus JDF by F naught. Figure of merit is defined as the ratio of signal to noise ratio output to the signal to noise ratio input in the message bandwidth. The figure of merit for various schemes can be tabulated as gamma DSBSC 1 AM K square Pmn plus 1 plus k square Pmn. Fm 3 by 2 beta square Pm beta p square by 2, where beta f comma beta p is the modulation indices of Fm and Pm respectively. Output of coherent receiver contains in-phase component of narrowband noise. FM receiver output contains quadrature phase component of narrowband noise. Figure of merit for FM receiver is 3 times or 4.7 dB superior to PM receiver. A random variable is a variable whose value at a time is a probabilistic measurement. It is mapping from the sample space to the set of real numbers. Cumulative distribution function CDF. Cumulative distribution function CDF of a random variable x is defined as fx of x equal to p of x less than or equal to x probabilities of cumulative distribution function 0 less than or equal to fx of x less than or equal to 1. Capital Fx of x is non-decreasing function. Limit extends to 0, capital Fx of x equal to 0, and limit extends to infinity, Fx of x equal to 1. Fx of x is always continuous from rights that Fx of epsilon equal to f of x. Probability of a less than x less than or equal to b equal to fx of b minus fx of a. Probability of x equal to a equal to fx of a minus fx of a minus. For discrete random variable, fx of x is a staircase function. For a continuous random variable, cumulative distribution function is continuous. Probability density function PDF of a random variable x is defined as the derivative of CDF, that is fx of x equal to d by dx capital of fx of x.